All right, so we're going to talk about how we can write equations for polynomials given a particular set of roots for that problem. Okay, so let's start out with a fairly easy one where we have a quadratic equation and we know that the roots are 5 and -2. So this is pretty easy to do because this means that I know in this equation that my two parentheses would have to be x minus 5 and x plus 2, right? Because when you set them equal to 0, that's how you get x equals 5 and x equals -2, right? So if I'm writing my equation, I'll make it y equals, then I can just take those and I can multiply them back together. That'd be x squared and then plus 2x minus 5x, so minus 3x minus 10. There is my quadratic function that has those particular zeros, and then we're all set to go, okay? So that's a pretty easy way of doing this one. Now, one thing to note with this one is that this is an example of a problem that has those two roots. Okay, but remember that all multiples of an equation have the same solutions. We are going to write the one that have relatively prime integer coefficients. Okay, so let's take a look at what we're talking about here. So this particular problem, right, if I'm thinking about what this looks like, we were told that the roots are at 5 and -2, right? So here's an example of a parabola that has those roots, okay? But it's not the only parabola that has those roots, right? I could also have a parabola that looks like this, right? That parabola would also have those two roots. Or I could draw a parabola that looks like this. That would also have those two roots, right? So there's actually an infinite number of parabolas that I could draw that have those exact same two roots, right? So there's an infinite number of equations here. And you could also think about this as just thinking about like your vertical shrinks and stretches, right? If I took that x minus 5 times x plus 2, right? If I stick a 2 in front of it, I have the same two intercepts, but now I'm going twice as high, or 3 times as high, or negative and 3 times as stretched, right? So you could keep tweaking this to make that work. Okay, so what we say when we're looking at these problems is that we're always going to make sure that we choose the equation that has relatively prime integer coefficients, meaning like there's no common factors you can divide out. Okay, so that's kind of the idea of what we're looking at here. Now, this guy right here, we've got a quadratic that we want to write where the roots are 2/3 and -1/2. So we could start this by saying, oh, well, that means it would be x minus 2/3 and then x plus 1/2, right? But that's going to be kind of a pain in the butt. I don't particularly want to do that problem. I'm going to have a bunch of fractions and it's going to be kind of messy. And then we're going to eventually want integer coefficients. Okay, so this right here, that's kind of the hard way. Okay, so here's the easier way of thinking about it. Instead of approaching it by setting it up like that, I'm going to kind of work backwards. Okay, so what do I mean by that? So typically when we're solving a problem, right, we start with something like x squared minus 3x minus 10 equals 0, right? And then we factor it, right? And then from there, we set each one equal to 0 and we solve, right? So what I'm going to do is I'm going to start at the bottom and work my way up. So I'm going to start with just x equals whatever my root's supposed to be. And then I'm going to backtrack my way up through the problem until I get back to the original equation. Okay, so that's going to be kind of what my plan is here. So I'm going to start this problem by having the answers x equals 2/3 and x equals -1/2. And I'm going to backtrack my way through it. So what would have been the step before this to get me to x equals 2/3? Well, I would have had to divide by 3, right? I would have been 3x and I would have divided by 3 to get my fraction. And then what would have been the step before that? Well, it would have been 3x minus 2 equals 0. Okay, so then I know that one of my two factors is 3x minus 2. Similarly, over here, what would have been the step before that? Well, it would have been 2x equals -1. And then the step before that would have been 2x plus 1 equals 0, right? And you can see that's the steps that we would take to solve it if we were going from the bottom to the top. Okay, so my factor here is going to be 2x plus 1. So then if I want to get the actual polynomial, all I have to do is just multiply these guys out together. So do a double distributive property, 3x times 2x, that's 6x squared. Then I'd have a plus 3x and a minus 4x. So that's minus 1x and then minus 2. And there we go. We've got a polynomial, relatively prime, right? There's no common factors. And that would have those two given roots. Okay, so it's all just kind of a backtracking. This guy, so we want an equation that has a double root of 3. So if it has a double root of 3, that means that I would end up with x equals 3, right? And it would be a double root, so I'd have that twice. So that means that before that, I would have had x minus 3 equals 0 for both of these. So it's just going to be x minus 3 times x minus 3 for my rule. So x squared minus 6x plus 9. And there we go. That one probably would have been an easier one to jump right to here and multiply it out. But I just kind of did the backtracking to show you kind of how that works. All right, this one, quadratic equation whose roots are positive and negative square root of 5. So again, I'm going to kind of backtrack this. So my answer is x equals positive or negative root 5. So the step before that would have been x squared equals 5, right? Square rooting both sides is where I would have gotten this from. So then the step before that would have been x squared minus 5 equals 0. And since those are the only two roots they gave me, there we go. That's my function. All right. This guy down here, so my roots are 2 plus and minus root 3. So I have two different roots. So again, I'm going to start at the end, right? So I'm starting with my answer. And then I'm backtracking. So the step before that, I would have brought the 2 over. So I'm going to make it x minus 2 equals positive or negative root 3. The step before that would have been square rooting. That's where that positive or negative came from. So it would have been x minus 2 squared equals 3. So then the step before that would have been x minus 2 squared minus 3 equals 0. All right, and then we're just going to clean this up a little bit. So x minus 2 squared, that's x squared minus 4x plus 4. And then when I combine my like terms, there we go. There's my function. Okay, so this isn't terribly awful. It's just a little bit different. So this guy right here, so my answer would be x equals 2 plus or minus 5i. So the step before that would have been x minus 2 equals positive or negative 5i. Okay, well, the step before that would have been square rooting. So it would be x minus 2 squared equals, and then this would have had to be, so we got a whole number 5 and an I. So the I means it would have had to be negative. And what number, when you square root it, gets you a whole number 5? 25. So that'd be negative 25. So then it would have been x minus 2 squared, plus 25 equals 0, right? And then we'll just clean that up a little bit. That's going to be x squared minus 4x plus 4. So x squared minus 4x plus 29 is going to be my function. And there we go. Okay, so that's how you can start with the roots and then work your way back and write the equation. Again, you could start this way every time. Like we could have technically even started that one that way. But that's going to be a little bit obnoxious. So I would recommend kind of doing a backtracking method. So think about like how you're doing the problem backwards to get back where you started from and just sort of follow that and you should be all right.